All right. So number 8, what's it say? Find the length of the curve, correct to 4 decimal places. Use a calculator to approximate the interval. So you really just have to set it up. I don't know if you guys remember, if you've done arc length before, the fact that the integral has a square root in it. Very first thing, giant square root in it, right? That's going to make it very difficult to have functions that are actually integrable by hand. Does that make sense?
Yes.
You guys should realize there's this big square root and there's nothing outside of it. There's no good chance for a chain rule to work, for example, because there's nothing outside to go with the d whatever and do stuff. Okay, maybe. So they want you to set it up. Let's see, number 8's got this beautiful vector function here. And they give me 1 to 3. Lock it. So what's the formula for arc length? Don't worry about that.
Integral of the square root of dx dt squared plus dy dt squared.
So in this case, it'll be 1 to 3 square root.
Dx dt squared.
Yeah.
Plus dy dt
Blah,
squared.
blah. Okay, I like it. Cool. So where's the question from? Do you remember how to use the calculator to do that? Is that no? Okay. So that's where we are. Okay. Let's set this up. You can pretty much see this directly, right? What's dx dt? Yay! And then you square it. All right. Say again. We're breaking r up into its components. I like it. Is that cool? So you have different formulations for this. R prime is all the components at once, but we just wanted to break it all up into its parts. I like it. Plus,
Negative e to negative t.
yeah, and then you square it, right? Is that cool? So it'll be, let me just put negative t squared plus e negative c, c e to the negative c squared. That looks yummy. Not to be completely honest, since it says use a calculator to estimate the interval, you can pretty much just throw that in there without, actually squaring it out and doing stuff. You can imagine that this might interact somehow, but right? Just for the sake of knowing that your teacher is a by hands kind of guy, let's go ahead and simplify this a little bit. So you get 1 plus e to the minus 2t. And then here, e to the minus 2t, so I get 2 of these. Now let me write another one of these just so we can look at it. It's not a big deal. So that's what we got there. That's why I put 2 of them there. And then here, what do I get here? These cross products. Yeah, I get minus 2 of them, right? So minus 2t e to the negative 2t. Yeah, I know. Only some old facts of life show, no? Yes? Too old? Okay. Facts of life. And then finally we get the last dude is going to be plus t squared e to the negative 2t. Yes. All right, let me stop there. Okay, so because your real question is how do you put them in the calculator and use it? Okay.
How many examples do you make us do this by hand, or would you say do it?
I depending on if it's doable by hand. I mean, can you look at that and realize that there really is no good way to do that by hand?
So if you're going to give us one and it says do it by hand.
There are some that will work by hand, but they're very few and far between. The functions have to be really nice. Again, the main problem is there's nothing here for chain rule, and and by parts wouldn't work because by parts doesn't work inside other functions. By parts is take entire functions as parts of it. So the bipartisan would say the entire square root thing would be one availability, one option to use for DV or U. It's like, well, screw you, biparts. Moving on, right?
Taylor series?
Yeah, you'd have to use some other, more advanced method to get some series answer for this, right? You could actually use modified substitution methods, but that I don't even want to think about that. So let me just show you, remind you, because this is good to know in general. If you can use your calculator, you might as well know how to check your integration. Excellent. And I love the animation they give you. So I got this little TI-84 emulator on here. You guys can have whatever your favorite graphing calculator is. Does anybody have an HP calculator, maybe? HP? Casio? You're all like, dude, you wanted TIs early. That's what I freaking did and kept it. I like it. Let me make this guy. Boop. All right. Gallery. Where am I? So let's plug this in here. Boop, boop. So I need that entire lovely thing. I lost my 1 there, but you all know it. Square root of 1 plus 2 e to the negative 2t. I just like to make you guys say that. Minus 2t e to... Did I have any? No. Oh well. Are you guys cool with the fact, of course, that there's an x there? Who cares? dt dx. 2t e to the negative 2t. You know it already, Jeff. And very small point here. If you're not that familiar with this calculator, possibly, there's a minus button and a negative button. That's one of the most frustrating syntax errors to get. And then finally, plus t squared e to the negative 2t. There we go. All right, so if you have the newer calculators, slim calculators are the newer ones, or maybe even some of you guys have a newer updated operation, your square root button just gets larger. The square root symbol just gets larger, which is nice. Right, I was jealous, but now I got one myself. So let's see, if we graph this thing, let's make the window correct anyway. I want to go from like 1 to 3, so let me go 0 to 4. And I don't know. I don't have a clue. So if I go to table, I get an idea of the outputs. Yeah, that's useful. There we go. Okay, I get the idea. Sure. I'm sorry I did that so many times. This is your reward for impatience. Alright. So at 0, it's yeah, okay. So I want to go x min, let's get x min 0 and x max, let's make it 2. Oh, I went to where? Where did I go?
1 to 3, right?
Yeah, damn it. Alright, here's how you... Well, here's how you blow up a calculator on your computer. I didn't realize I was going to show you that demonstration. Oh. Where did I go? Oh, good job, Jeff. 0 to 4. And then y min will make it 0 to 2. I like it. Y max 2. There we go. This is really exciting. Now, some of you guys have seen this before, but this is, if you haven't, I can't believe, I don't know how long you've had this computer, but if you go to second trace, go to calc. This is where you do stuff like minimum, maximum, but you can also do integrals down here, number 7. So integrate from 1 to 3, and it even shows you visually what the hell you're doing. It's nice. Oh, oh, thank you, calculator. Okay. So I mean, that's beautiful. So I could ask you to do something like that on your calculator on the test, because I want to see you set it up, and I want a more interesting function. Maybe I have you do other things with the function, and in that case, it's got to be interesting, which almost always means the integral will be either really difficult or impossible to do in closed form, right, by hand. I like it. So you've got technology existing for a purpose. You can also just check your integrals that I make you do by hand. Check your answers for integration. Yes, no, maybe so. You can do dy dx too. Did you notice that? At a specific point, you can find the derivative of the tangent line at that point. Yes?
I did the same thing you did by 2.01.
Oh, your calculator just is more generous? I don't know. Oh. And you did, when you integrated, you put in there 1 and 3, right?
Yeah.
Okay. There might be just a slight difference in there somewhere.
I can't do it exactly like you did.
All right, you'll have to. I have no idea then.
This isn't one back right wrong. Then.
It would be, but I can't tell right now. You have to show me later, so I can figure out exactly what it's doing. It could be me too. Oh yeah. We'll take a look. Did somebody else try that? Anybody else get that? Yes.
I got the same answer.
Okay. Ooh, I like it. It's blue. All right. You can change the color if you like. If there's certain colors that offend you. All right, like red. You're all like, oh God, he's wearing red. All right. Anything else from? Is that cool? Whoever asked that? I mean, that's a good thing to know how to do. Any other questions from homework stuff yet? Okay. So let's see. We left off. The last thing we did, we talked about the unit normal vector, right? To a vector function, to some space curve. So the very last thing we talked about was this, the unit normal. I think, yeah, they do. The bottom of page 907, they kind of gather up, because like I said, there's like an avalanche of equations that just happened. Right. I'll show you an animation here in a minute that's got this. But kind of the last piece of this that goes into motion of a particle or whatever that's defined by this vector function, the space curve, is what's called the binormal. And this is the cross product between the tangent vector and the normal vector. Cool, I like it. So, if you are going into anything related to aerodynamics or even space exploration or anything dealing with kinematics, the motion of particles or motion of objects, it's possible you can talk about what's known as a TNB frame. Somebody tell me something about TN and B. In fact, N, let me see if you guys remember. I think we talked about this last time. How is N related to T? Let's start there. I don't know if you guys remember. We had a little discussion about why this is true.
It's perpendicular.
Perpendicular. I like it. So that's we like to break things down into the tangential. So it's sort of like breaking things down to X component, Y component. Are you with me? Because we have those existing axes, and we're going to use those existing axes. But if I'm just in space, there's no existing axes. I got some vector. I can have some other vector and say, I want the part that's tangent to that, lying in the same direction as that vector, or normal to that, or orthogonal, perpendicular. So many words for that idea. Must be an important idea. So T and N are perpendicular. And obviously, B is how related to T and N. Also perpendicular. So T, N, and B form sort of like their own X, Y, and Z. that the whole thing turns as you move along. So let me show you this kind of cool little animation. Oh, where is it? For some reason it's Explorer that works well. I guess it has to have something it works well for. Here's that unit tangent vector. I think we're all kind of cool with that. And that's from calculus 1. But if they give us a curve, three-dimensional curve, then I bring into play it can point in any direction depending on which way the curve is actually turning. You guys kind of with me here? So we're used to the tangent, the idea of the tangent line in 2D, XY plane. We can do it. We can even estimate how to draw it as it go around a parabola, and it's like that. Whee! But once I introduce a third dimension, then I introduce the chance that my function is moving this way now, and the tangent vector is going to turn that way with it. So what's nice about these animations is I can actually turn this thing around, so I can see what the hell's happening as it goes around this turn. There it goes, and now it's on the far side. Oh, poor little lag. So it's always following, pointing the direction that curve is going. Of course, the curve is going in, it's rotating through all three dimensions, right? I like it. How are we doing there? Is that decent? So that's a little leftover thing about the tangent vector. I like it. And I don't think this is I'm not sure if there's yeah, it is a unit tangent vector. Okay. Here's the TNB thing. And in fact, if you're at all interested in any of those subjects I just listed out earlier, you should search TNB frame. And I think there's a problem. I don't think I assigned it, but too bad for me and you. There's problem 62 on page 910 that talks about the Frenet-Serre formulas. Frenet-Serre, I can't remember how to pronounce that first one, to be honest. And they're kind of cool. They introduce the idea of torsion of a curve. So how the word torsion kind of feels like this. How much the corkscrew is happening. How tightly the curve is curving in all the different dimensions, not just the curve itself there, but because you could be curving back on itself, you could be doing all kinds of things. So the torsion is a more general idea of curvature, and that's involved in these formulas. All right. Yes?
Can we call the binomials TNB?
You could, anything you want to. Will I call it that? No. But, yeah, I don't think so. But you can call it whatever you like. Some of you guys call things, several things under your breath. I know you do. Sometimes I might use similar. All right, so watch. So this is really kind of cool, but it's not the most immediately understandable thing, that's for sure, and you guys know how that works. So here I got my unit tangent vector, purple. That's the one that makes the most sense. Does everybody agree with that statement? That's the one we've known forever, and just because I introduced one more dimension, it's still going to follow wherever the hell that thing goes. It's going to point the direction it's instantaneously moving, so that makes total sense. The normal vector is just always perpendicular to this, and it's the one that actually, yes?
It'll point inside the curve.
Exactly. So if I'm curving this way, in fact, I'm going to show you that here in a minute. If I'm curving this way, you'll see that the orange vector will be pointing in. And then the minute, so there's an interesting place. Let me see if I can find somewhere it does this. Maybe it's not the best. This is not the best one for it. But just to show you what's happening here. From that direction. See that orange curve, that orange vector? So it's going to turn and always point inside. It's sort of like if you drew a radius, it would point this way. You would never draw a radius coming out of the circle. That wouldn't make any sense. You'd always draw it in here. Is that cool? So that orange vector, oh, let me turn off some lights. All right. That's a little better. As always, so let me find something that's a little more interesting. That's very interesting. All right. All right, Jeff. I'm gonna guess it. Okay, stop. So now watch that orange vector as it goes around right here. This point right here. This is a point that we're all very familiar with in calculus. What would you say the concavity of that was if I was just thinking about 2 dimensions? And let me turn it like this. I know my XYZ is all turned around because I am not. This is why I should never be a pilot. Okay, let's do it this way. Here we go. So I got my XY plane kind of like where it should be. That was my fault. I had the whole thing turned upside down. My Z is pointing out upwards like it should be, like you guys should make it standard positions. This would be like concave down, right? So it's pointing in. This is concave up. So right in the middle is that weird ass inflection point. So somehow it's obviously it's going to have an analogy to the inflection point for 3D. And you can watch that orange vector go a little bit insane. You can do this. All right. So now it's all happy. It's like there's a definite inside of that curve, and then right around here is like ah. But the direction it rotates actually is related to how that curve is changing. Yes, sir.
It doesn't look like it happens instantly, so it's more like...
Yeah, it can't happen instantly, right? Because the curve is nice and smooth and continuous, so it's not going to happen instantly. It's as there's a less well-defined interior of the curve, it's got... Let me see if I can find a nice place. Can I zoom in? No. Oh. Hello. Let's see. So right there, it's still good. And then right here, this whole transitionary period, you see right in the middle is where it's very linear. Right? So for a straight line, which direction would that orange vector point? Well, that's where things get weird. I like it. So I don't know if they gave us that option here. I don't think they did. They didn't give me a nice straight line. Too bad. But for a straight line, what's happening to the... Let's see if I can, what was that one? That one was cool. Is it good to me upside down? No, I made it upside down. Alright. Oh, everybody's cool with... Okay, the purple is the tangent. The orange is the normal. And the blue is this new binormal. And together they're supposed to make their own little, well, it's what's called, together they span the space, so they can create any vector in 3 space, but it's just because they mimic the XYZ axis. So I can actually have this animate and track. As it moves along, you can track this. And I know it's a little bit, it's kind of nifty as hell. Weehaw! So as long as the curve is not changing, as long as the curve is staying the same, then that's going to have a good time. The minute there's a transitionary period between curving one way and curving another way, and of course there's 3 dimensions in which your curve can change. Are you with me? So it could be curving, and then it could be, and then it could curve this way. So the orange line is going to also react to that change. So anytime there's a change, it's going to have to go through a transitionary area. I like it. It's kind of freaky. Anyway, all right. Stop. I think I can, if somebody will email and remind me, I think I can send you guys the direct link, even if you don't have WebAssign, you can actually still access these. We'll have to try and see. I think you should be able to, because I'm not currently logged into WebAssign and I'm accessing all of them. So that's something I didn't know I could do, to be honest. So I think I could probably send it to you, and you can access all these animations and sit there and go, well, that was neat, but I still don't understand any of it. A phrase you're probably going to utter a few more times. We haven't talked about this yet. No, so we're going to talk about that next. All right. I didn't. You missed all of that. It's too bad. So, how much of this do you have to worry about right now for this class? Not a lot. I need you to be able to calculate these things. I need you to be able to answer basic conceptual questions. If I gave you this and I said, which direction would the tangent vector be pointing, you should be, if I gave you this kind of problem, I said, all right, here's a slice of something that is in the xy plane. At this point, which direction would the tangent be pointing? You should be able to draw all that in. Which direction would the normal be pointing? You should be able to draw all that in, right? And what gets interesting is, why is it important, the ordering of this?
It's always pointing in the same direction.
Well, so why is the ordering of these two important?
Because it changes the direction.
Yeah, it changes the direction. So if I ask you which would this be pointing into or out of the page, you just have to think about, well, what would T cross N be? And that's where that right-hand rule comes into play.
Out of the page.
So in this case, so right here, this would be what? You could do a better job than that, sure. This would be T, this would be N, and it's T cross N. So if you take your right hand, put along T and then curl towards N, it's going in. I like it. Are you guys? That's how the right hand rule works. I think a few of us weren't still sure about it. So T is first, put your right hand in the direction of T and curl it. So if N was pointing this way, I'd have to do this so I'd be able to curl in the direction of N.
Yeah,
but to curl in the direction of N, I have to do this way.
Why is it not pointing up there?
Why? Because it always points the direction inside the curve. I like it. So here it would be, there would be the tangent. So I'm assuming it's moving in this direction. There would be the tangent, there would be the normal. And now
The reason it's pointing inside the curve is because it's basically, if you think of it as acceleration, that's
Yes.
how.
In fact, if you look at the formula for N, it's got acceleration in it. N is sort of related to acceleration. When you have circular motion, your acceleration is always into the center. So something orbiting the Earth is what's pulling it. It's providing that acceleration, changing its velocity. So the acceleration is directed inward. So that's a nice physical reason why it's pointing in. I like it. How are we doing? So let's do this. Let's take a second. Let me write up on the board in case you don't have the book with you. I just want, so here's a couple of formulas here. Let me remind you a few more formulas. What else we got? Do I already have that up here? Yes. B I've got up there. Who cares about curvature? Don't stop that. So let me give you a vector function. Give you one that's not too evil. Nah. Yeah, I like it. Sure. Yes, cool. I like it. This should become kind of very familiar. This is a classic, easy thing to get a hold of. What would this look like?
Spring.
Spring. I like it. Thank you, Dan. I saw what you're doing back there. And I desperately want you guys to be able to realize these are the ones that are curvy. This one is purely saying don't just draw a circle in the xy plane, step away from it as t increases. So you're continuously stepping away from in both directions because t could be negative. So that's what you want to look for in how to break these things down. I like it. So try to calculate all of these things for that. It should be relatively simple. It's a nice circle. Are you guys understanding what's happening? I want you to calculate the normal, the binormal, and the tangent vectors.